Hi, I'm Yuki Miura, a PhD student in civil engineering at Columbia University. Today I'm presenting Liz.
Chen Yang Ryu. I'm also a PhD student in applied math in Columbia Engineering.
Hi, I'm Phil Denenis, a PhD student in applied math at Columbia Engineering.
So we are presenting protecting coastal infrastructure in a changing climate by integrating optimization modeling and stakeholder observations. In New York City, back in 2012, we experienced a massive damage from Hurricane Sandy. It was flooding and power outage. In New York City, also, we expect that having sea level rise until 2080s, at least we should expect that 12 inches of sea level rise. And if we consider a rapid ice melt scenario, it could go up to 55 inches. To protect the city, we have so many kinds of possible adaptation strategies, such as seawalls, rising buildings, barriers, having artificial dunes, and strategic retreat, and so many more. And these huge variety of adaptation strategies are available at multiple scales, what, where, and when. So we are proposing optimization methodology for those protective strategies. First, we will start with parameterization of protective measures, and based on those strategies, we're going to compute the flooding, accounting for sea level rise. We have two models here, GIS and GeoClaw. We will discuss in detail later. And based on the flooding estimation, we will compute the damage. And also, we're going to check the strategy's suitability based on the stakeholder interviews. And then once we find optimal strategies, this loop will end. Otherwise, we're going to continue to find the optimal strategy. We are focusing on these target areas in New York City. There are some vulnerable areas such as Lower Manhattan, Staten Island, Brighton Beach, and Rockaway. So we start with parameterization of protective strategies. And first, we will start with GIS model. GIS model is high speed and very simple model, starting with generating artificial maximum storm surge. If there is a time history of storm surge, we can definitely use that as well. And generate the coastline segments with potential protective measures. And then we're going to compute the overall flooding volume coming into the area. And then eventually we will redistribute this volume of water over the area. And to see the efficiency of this model, we use the Hurricane Sandy's actual inundation area that's colored in dark blue, and simulated inundation area is bright blue color. So for this simulation, it took actually 0.001 second in Lower Manhattan. So we can say it's pretty accurate given the computation time. And another computation scenario, Hurricane Sandy without any protective measures in 2050s, 2100, we can see inundation area was expanded without any protective measures. And if we have some wall, like 2-meter height wall along coastline, colored in red here, in 2050s, 2100, we experience actually pretty massive flooding here. GIS model has also capability of simulating subway system. This case is Hurricane Sandy without any protective measures as well. Red line shows flooded line of subway. Green line shows no flooded at all.
Hi, Chanyang and I will talk a little bit about the GeoClaw models. GeoClaw is a solver for shallow water equations, and we're using this to complement the GIS model. The storms are derived from a climate conditions, so we perturb the sea surface temperatures. This differs from GIS, where the storms or the surge heights are statistically drawn from a probability distribution. It's computationally expensive, but because it is based on physical storms and shallow water equations, we think that the simulations will produce more realistic results. We can also model different strategies by placing storm surge barriers in water, which is something GIS cannot do. Here is an example of two different storms derived from ensembles. They have different trajectories and intensities as parameterized by the Holland 80 model, with parameters such as maximum wind speed and central pressure. And here is a simulation of Hurricane Sandy hitting New York in the absence of protective measures. And here is an example with one of the proposed protective measures, which is a storm surge barrier at the Verrazano Narrows. We can see which places benefit from such a measure, but also which places might be worse off due to the redirection of water.
To see the accuracy in GeoClaw modeling, we look at the Sandy storm surge height, and on the left is the actual real data, which was about 2.8 meters, and on the right is the GeoClaw prediction, which is 2.2 meters, so it's around the same scale. So what we need to do now is we need to run the GeoClaw simulation with barriers, and that is a work in progress. And that's because there is a computational problem, a challenge that we cannot refine down to 10 meters of scale structure, which is the barrier. Barrier is going to be very small compared to the whole landscape of Manhattan. And so what we're going to do is impose a computational a barrier where we want to place it. And solving that problem requires us to use a more special method called H-box method. And on the right, we see a simple implementation of that, where it's a flat barrier, and I drew a little red line to show the wave front, what the wave is doing, is overtopping the barrier there.
So based on those flooding models, we will compute the damage. Damage cost estimation, we need an input as building information, subway system, and their elevation data, and also flood height and duration from the flood modeling. And we put this into damage function, which accounts for economic loss due to inoperability. We will get the damage cost. And here's some example of damage cost analysis for Lower Manhattan. Here it's for 2020 to 2100. On the left side, we don't consider any protective measure, and we also have 2-meter height wall along coastline on the right side. So we see that the damage cost could go up to 90 billions from $40 billion without any protective measure, while we have this 2-meter wall height. And then if that's the case, the damage costs go down significantly, reduced up to like $10 billion. But of course, we have to check the suitability of this because we have like limited budget. So we input the stakeholder interviews. We've been working with stakeholders such as New York City Transit, Emergency Management, Mayor's Office, the Port Authority, and also fire department directors. And this is a diagram of interdependency of those sectors based on their inputs. As you can see, it's very complicated, and our current issue is to implement this into the economic, social damage, and we will be working on this. And based on those, eventually we will find this optimal strategy. And to find it, we start with GIS model. And then to fine tune the optimal strategy, we will use the GeoClaw model. And here, optimal protective strategy is in over time and space, and also that reduce maximum reduction of losses given prescribed budget. And this is our summary of the work and future work. Thank you very much for listening.